ticks, but behind this there is a mechanism that makes it. In the clockwork in mathematics, want to know what's the mechanism behind mathematics that makes it. Ooh. Let's begin firstly with a question, because mathematics is not a clock, right? Where can we find mathematics if not on the wall, like the clock? There are two possible places we can search for it. One is in our minds, the other is outside. So, where do you think mathematics is? Is it in the human mind, or is it outside in our surroundings? Outside. You think it's both? Nobody thinks it's inside.
Everything. Every object you look at, you see that's in.
So is it around us?
In us, around us. Definitely.
Fantastic. We've got some famous quotes to compare our answers to. The picture on the left side you see is that of Bertrand Russell, who was a logician and philosopher. There is a movie called Man Who Knew Infinity about Ramanujan. And one of the characters he was finding in that movie is Bertrand Russell. He says that the pure mathematician, like the musician, is a free creator of his world of ordered beauty. It kind of seems to suggest that mathematics is inside. Then Richard Courant, who worked in analysis of mathematical physics, says that mathematics is an expression of the human mind, reflects the active will, the contemplative reason, and the desire for aesthetic perfection. All these three things are also something that's within us. But as you rightly remarked, at the same time, mathematics is also outside, and here are some quotations to back that. Katherine Johnson worked for NASA. She says that some things will drop out of the public eye and go away, but there will always be science, engineering, and technology, and there will always, always be mathematics. Without mathematics, there is nothing you can do. Everything around you is mathematics, says Shekuntala, who was a mental calculator. Do you know what a mental calculator is? It's a very extraordinary ability of a human being to calculate large numbers. And she was very, very famous with that skill. You see, she says everything around you is mathematics, like she said. So mathematics is everywhere. It's both in the subjective real within us and also in the objective real around us. But in a way, it's hidden. Even though it's everywhere, it's kind of hidden. It gets activated, though. It gets activated by exchange of these two realms. And this is a fragment of a picture by one of the Italian painters. On the picture, you see Euclid explaining some mathematics to students on iPad. That's what my daughter thought when she was 4 years old. She looked at the picture. She already had a good knowledge of what iPad is. Not that much of Blackboard. Well, one can argue actually that piece of paper or a board is already kind of some primitive form of a computer, because you're able to record information on it, store information on it, and use it to do computations that otherwise would be difficult in your mind. So I put this picture to symbolize the exchange between the two reals. But now let's look at an example of it, because we want to uncover what makes mathematics tick through contemplating on this exchange. So here's a little problem. Katri, Maya, and Zuri were throwing a party. Each car brought 6 guests. Once all guests arrived, there were 33 people at the party. How many cars were there? It requires a thought, right? You need to think about it a little bit. Of course, mathematical notation makes the thinking easier. You can set up an equation. If x represents the number of cars, thing we want to find, each car brought 6 guests. So the cars altogether brought 6 times x. Then you guess. There were 3 hosts. So 6x plus 3 should give the total number of people, which we were told is 33. So that's the equation we kept, isn't it? And we want to find x. It's not difficult to find x. If 6 plus 3 equals 33, then 6x must equal 30, right? So then x must equal 5. So the answer is 5. There were 5 cars. All right, so this is a very simple process. Everybody can do that. But we underestimate what's going on here. Because actually, there are 2 ways you can do this. One, you do these steps because your teacher told you that's how you solve the equation. So you apply the steps and get the answer based on what the teacher said. So you need to have a good trust in your teacher that they told you the right rules. The other, you rediscover this yourself, these steps. And even though the steps are easy, it's not so easy to discover. In fact, in many ways, mathematics is all about that. Discovering for the first time is very difficult, but then you discover things that are easy to work with. That's how mathematics helps with real life. It makes life easier. So let's see what's actually happening in our mind if we honestly believe that there must definitely be 5 cars, and that's the only way. Then, in this exchange of the objective and the subjective, we arrive to something which is much more complex. So we're going to spend some time on this slide. When you're looking at the equation, the first line there, you've got something strange here, right? You've got x. What is x? It's a variable. But people didn't always know about this. It took a while for human beings to think this way. So let's try to go back to our thinking and ask ourselves this. Then the answer to the question would be the following. It is given in step 1. Assume that x is a specific number. It must be a specific number. It's the number of cars, right? So let's assume that x is a specific number before we assign it in the value. It can be any number because we don't know yet how many cars we've got. Whatever we'll say about x in what follows will not make use of any specific fact that depends on what the number x is. We want to be as general as possible, not to exclude some possibilities of missing out the actual number of cars. So we're starting off in the first step with x that symbolizes any number, potentially any number. But at this stage, right after we move on from step 1, we're thinking of x as a specific number. Of course we are, because had we not been doing that, how would we be able to do arithmetic with x, right? We did some arithmetic with x, so we were treating x as a specific number. But this specific number, x, could be any number before it became specific. right? So there's already a lot going on there. So that's the first step, where in this first step, we bring in the x. We don't know what it is. It potentially could be anything, but we're going to work with it as if it was one specific thing. What's step 2? Now that x is the x that comes from our problem. It's the one that satisfies the equation 6x plus 3 equals 33. Is step 2 a logical consequence of step 1? Remember, in step 1, x was any number. X equals 0, for example, would work. 0 doesn't satisfy that equation. So step 2 is not a logical conclusion of step 1. Step 2 is instead an additional assumption on x. We began without any assumptions on x because we first wanted to introduce the variable. We just assumed that x is some number. And then in step 2, we're making another assumption. We're assuming that it's a number that satisfies the equation. Okay? So every time I make an assumption, I add an assumption. Every time I do that, my bars, these bars that you see displayed here vertically, they go inside. I want to track them because at the end, I want to get rid of all my assumptions. I want my final conclusion to be independent of any assumptions because I want universal truth. But as an aid for arriving to universal truth, I'm introducing some assumptions. First, that x is any specific number. The second, that x satisfies that equation. In step 3, we say, then 6x equals 30. We no longer say assume, right? We say then. What's the difference between assume and then? Then refers to logical conclusion. It means that I'm certain now that what I say in step 3 is correct based on my previous assumptions. How can I be so certain that 6x equals 30? Because the teacher told us? Well, yes. But that's not good enough. We want to ourselves also understand why is 6x equals 30? And the explanation is simply that you begin with that number, the two numbers, 6x plus 3, that was told us to be equal to 33, right? You've got equal quantities. If you subtract 3 from both sides, they will remain equal. So we subtract 3 from both sides, we get 6x on one side and 30 on the other side. That's logically quite certain. We don't need the teacher to help us with that. We then make another conclusion in step 4. We say, then furthermore, x must equal 5. We've got two equal numbers. We can divide both numbers by the same number. We'll get the same result in both cases. So dividing both sides by 6, we get from 6x we get x, and from 30 we get 5. So that's clear for everyone, right? But now something interesting happens in step 5. Now we say, so if 6x plus 3 equals 33 is true, then x equals 5 must be true. And notice two things that are different now. Firstly, the bar has moved left. And secondly, there is a statement here which says if something, then something, but kind of weird because in step 2, we already assumed that 6x plus 3 equals 33. Why didn't you say if this, then that? We already assumed this is true. Why would I repeat myself? So these two things are related to each other. What happens in step 5 is actually I'm dropping the assumption I introduced in step 2. I introduced this assumption that 6x plus 3 equals 33. I derived a conclusion from it, And now that I know that I can do that, I don't need my assumption anymore. Now I can state the universal fact that if 6x plus 3 equals 33, then x must equal 5. And because this bar no longer depends on the assumption, we've now moved left. We now want to move left one more time. We want to get rid of all the assumptions because at the end we want universal truth. So let's look at step 6. No matter which number x is, if 6x plus 3 equals 33 is true, then x equals 5 must be true also. What makes us say that? If you go back all the way to the beginning of this bar, we said there, assume that x is any number. And for that arbitrary number, we derived that if this is true, then that is true. That means we've proved, we've kind of validated that no matter what x is, if this is true, that will be true. That's what we say in step 6. And for step 6, we no longer need to assume anything about x. We're now making a universal statement about x, whereas remember in step 1, after step 1, x became a specific number. If x were a specific number here, we wouldn't be able to make a universal statement about x because the universal statement means that it should apply to all the numbers. And finally, from step 6 to step 7, we kind of rephrase what we say here. We say in step 7, the number x equals 5 is the only number such that x plus 3 equals 33. Does that make sense to you? So if no matter what x is, if this is true, then that will also be true. That means that x5 must be the only one that makes that true. Because in step 6, we're saying every time this is true, that will be true. So this must be the only way this is true. Now at step 7, we've come to the conclusion that x equals 5 is the only answer. There cannot be any other answer. Whereas here, we knew that x equals 5 was an answer because the teacher told us we can do it like this. But had I asked you, how do you know it's the only answer? It would be difficult maybe to answer the question. In fact, how do you know it's the only answer? That question has this as its answer. So we can be absolutely certain that there are 5 cars. If we now look outside and we see 6 cars, something strange. If you see 4 cars, one of the cars was stolen. And this certainty is what mathematics is for in terms of our life, in terms of applications of mathematics. That's what it's for. It's for certainty. It's to be able to do things that we can be sure of. Okay, let's rewind back now a bit. So what I've shown you here is the movement of mathematical argument. This is the same picture we saw before, but I just rotated it to highlight these blocks that represent assumptions that have been introduced or that have been dropped. And as you see, just like in a clock, where you've got these wheels, some of them are small and some of them are big. You've got those horizontal lines, some of them are vertical. Some of them are small, appearing under the big ones. So there is this structure that mathematical thinking has. And just like these wheels are the things that make a clock tick, this structure of mathematical thinking is what makes mathematics tick. But mathematics is not the only place where we find such structure. A structure similar to this also exists. And we're going to learn how to identify that in this session. So I'm going to play a video of a pianist playing Beethoven's Janelidze. I guess you all know which one I'm talking about. It's da 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 da. The diagram you see on the left is the structure of that piece, which is in a similar correspondence to the structure we looked at for the mathematical argument. You see there are also horizontal bars. Every time a musical idea completes, we move on to the next bar. And these bars line a hierarchy, just like the mathematical statements lines up in a hierarchy. We're going to see if we can pick up the bar structure and identify as we listen to the music. So every time you see that red dot with the smoke coming into play, when you think that the music hits that bar, you clap. And I'm going to indicate to you, when I hear a clap, I'm going to indicate to you whether you clap right or you clap wrong. But before we do the clapping, I'm going to first show you with the pointer how it works. And so the idea is if you can continue. Sorry, the best way to do this is for me to stand at the screen. Did you get it? Okay. So let's play again, and when the music hits the first smoking bar, clap, please. Ayun. Missed it. You missed it? Oh, well, that's how we didn't miss it. Okay, the internet is giving us some time to reflect. We were here to get an idea. Well done. So if you're a bit lost, you can also observe the higher level bars. They kind of mark end of section. All right, maybe we should come back to this a bit later. But it wasn't bad. We did it well. So this is a summary of what we did so far. What makes mathematics tick is the causal structure of thought. Now, why do I call it causal structure of thought? What is clause in languages? Clause is a phrase that contains a verb. But you can have complicated sentences as well, clauses that contain subclauses and so on. So once again, we find similar structure of hierarchical structure of the entities that make one and their sub-entities. But now the verb in the language is a very important thing because the verb marks motion. Something is happening. So in both cases, in the case of music, where each bar, each black bar there, was representing a piece of music which had some kind of emotion in it, something active happening. In a similar way, in the mathematical argument, each of these bars tells a story. Something is happening there. And then an overall thing happened here when we went to the higher level. And so basically, the structure that we're talking about here is the structure of significant things happening during the process of mathematical thinking. And that's why we call it causal structure, to borrow the term from the language where cause represents a phrase of the verb. We underestimate often this aspect of mathematics because for somebody who is talented in mathematics, these structures arise almost subconsciously. But for someone who is maybe in the beginning, because it's impossible not to develop mathematical ability, but in the beginning, one person might be showing less ability than another. That's possible. And what I'm trying to say is that what's behind that is that these structures, these causal structures, are not forming so easily for that person as it is for the other. But of course, once we know what structures in our brain is to form, we can focus on that to develop the skill. But there is something non-trivial going on there. Unlike in music, where basically you can continue your musical piece almost in any way, you can't do that for mathematics. You cannot continue your mathematical argument anyway. There are some rules, very few of them, but there are some rules. Continuation, and I want to demonstrate that to you now. So here we have a sequence of numbers, 1, 2, 3, 4, 5. What's the next number? Let's start writing this down. Some of you say 6. If you think it's 6, can you please raise your hand? I would like to see how many of you are giving a vote for 6 so I can record it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 votes for 6. Any other numbers? And please, Dr. Lasco, tell us that. It can be any number. Any number. Students say arithmetic sequence. So the point that they're making is the point I wanted to make too. There are many ways to continue that sequence. 6 is not the only way. Here is one other way. We all know what prime numbers are, right? A number is prime if you cannot present it as a product of two whole other than itself and 1. So you see 1, well, 1 doesn't count as a prime number, so let's start with 2. 2 is a prime number, 2 equals 2. We cannot decompose it further as a product of two whole numbers. 3 equals 3, 4 equals 2 times 2, 4 is prime. Because it's 2 times 2, 5 cannot be decomposed. 6 equals 2 times 3, 6 isn't prime. 7 equals 7, can't be decomposed. 8 can be decomposed in products of 3. 9 is 3 times 3. 10 is 2 times 5, and so on. Now, the sequence that I had in mind, it can be any sequence, but it was a riddle. I had a certain sequence in mind. It wasn't a mathematical question. The sequence I had in mind was numbers that are powers of prime. So it's a single prime multiplied by itself several times. So all of these are valid, but this is not valid because there are 2 different primes we multiply. That's why it's red. 6 is going to drop out. 7 is valid. 8 is valid because it's 2 times 2 times 2. 9 is valid, 3 times 3. 10 isn't going to be valid because it's product of 2 different points. So you see, another way to continue that sequence would be to have, instead of 6, to have 7. But the comment that was made about the fact that it could be any number is actually a very valid comment. We didn't have sufficient amount of assumptions about our sequence from 1 to 5 to know for sure what the next number would be. So here's an example of a mathematical argument going wrong. Assume A, B, C, D, E, F, and so on is an arbitrary sequence of numbers. Just like before we assumed X was an arbitrary number, now we assume we have an arbitrary sequence of numbers. Assume furthermore that the first of these is 1, the second of these is 2, the third of these is 3, the fourth is 4, 5, and these are the only 2 assumptions we had, right? And then we say it's 6. But now how are we going to explain this? Remember, if some line is not an assumption, it needs to be logically motivated. Those of you who said it's 6, and there were 9 of you, how would you explain why is it 6? Why does it have to be 6? That number of cars there had to be 5. we managed to explain it. What about explanation here? Yes, sir.
The pattern. Because starting from the beginning, we're adding one each time.
But didn't I show you here another pattern? This is also a pattern, a different count. Now, how did you know which pattern to use? Does that make sense? If you look at the assumptions, there's nothing here that restricts the pattern. There's freedom for the pattern to be added. And yet at school, and sometimes in the university, so often this question gets asked. What is the next number? And in all the cases where this question gets asked, students will say it's 6. They're marked correct. And what do we learn this way? We learn this way to do mathematics by guessing without being able to validate our guess. We learn mathematics very opposite to what makes it tick. No wonder then, after a few years of learning mathematics like this, mathematics doesn't tick anymore. Instead, it tickles. I'm going to be slowly concluding. I want to conclude with a few famous quotes. Mathematics knows no races or geographic boundaries. For mathematics, the cultural world is one country. David Hilbert is considered as one of the greatest mathematicians of all time. And he said that. Another mathematician who is considered to be one of the greatest mathematicians of all time is Carl Friedrich Gauss, who said, and this is very, I mean, the left-hand side one feels very correct. I mean, it doesn't feel like, oh, really? It feels like this is how it should be. But look at the right-hand side one. If others would but reflect on mathematical truths as deeply and continuously as I have, they would make my discoveries. A person who is considered to be a mathematical genius tells us there's no such thing as genius. You just have to be slow, reflect deeply, reflect continuously, don't waste too much time doing other things. Be continuous on your reflection, and you will make the same discoveries I have. Mathematics will start ticking for you. John Wesley Young. It's clear that the chief end of mathematical study must be to make the students think. In South Africa, we have pure mathematics and mathematics literacy. What's the difference between these two subjects? The content. Now, John Wesley Young is saying, when you teach mathematics, you shouldn't worry about the content. You should worry about the thinking skills. Which is quite aligned with what we said today about what makes mathematics tick. So I would like to dream of a mathematics curriculum that brings together pure mathematics and mathematics literacy, that gives everybody an opportunity to reflect continuously and deeply on mathematics, like Gauss did. You need opportunity for that. You need time to reflect continuously and deeply on something. You can't do it in a rush. And that doesn't care on whether you're learning trigonometry or you're learning quadratic equation. What it cares about is that you're learning the secrets of mathematical thinking. Shakuntala Devi said, why do children dread mathematics? Because of the wrong approach, because it is looked at as a subject. That's a very interesting statement. One can talk a lot about what it means, right? Subject is something you absorb. I think what she wants to tell us is that mathematics is something you do, not something you're forced to absorb from and then give back on the exam without keeping anything for you. It's an activity. It should be something that you do through which you acquire the thinking skills. We refer to that one. Mathematics is not about numbers, equations, computations, or algorithms. It is about understanding. It's very similar to the other one about thinking, right? In mathematics, the art of proposing a question must be held of higher value than solving it. You see, asking questions is what will take us from here, applying a routine algorithm to solve the problem, to here, expanding on explaining why is every step a valid logical conclusion of the previous one. And we have a couple of more quotes there. The only way to learn mathematics is to do mathematics, which we already touched on earlier. Well, I would like to also share with you some good news. We have something called Future Mathematicians Program, where we try to implement this vision of mathematics that was summarized in the course above into an extracurricular mathematical activity. If you're interested, go on the website called futuremath.net, and you can find more about it. You can also get in touch with us. Thank you.
Thank you very much, Professor Janelidze. It was a very enjoyable talk. Pretty deep. Seems like it was simple at the beginning, but very quickly mathematics will get deep. But he welcomes questions, so feel free to ask anything that's on your mind that you want to clarify. Yes, sir.
I've read somewhere about some research into Fourier analysis, Fourier transforms. So with respect to memory, with respect to the brain, basically, like when we, if we recognize a person, like we've seen after 20 years or something, you know what I mean? Our brain recognizes them immediately. So basically, what happens is our brain like uses a Fourier transform and stores that information as a hologram, basically, and something like that. Are you aware of that?
No, but it's very exciting what you're saying. It's very interesting. Yeah, I mean, so I think one of the next steps for mathematics is to figure out human brain.
And I've read that it's already been done, basically.
Not all the way, right? I mean, figuring out human brain means really like fully figuring it out. So
Mapped it out, yeah.
Yeah.
Well, there are some people that study this deeply, actually. We attended a conference, what was that guy at Ayukawi early 2000s, 1,000 people outside. Oh, Roger Penrose, yeah. Roger Penrose, perhaps one of the most prolific living mathematicians, he was giving a public talk in Pune in India. There was a conference on, but so some of the conference delegates went, and there were 1,500 people in the auditorium, not like this 30 people. 1,500 people in the auditorium, and there are 1,000 other people outside shouting, wanting to lynch the organizer because they can't get in. And ordinary people, taxi drivers, housewives, and any kind of worker. And he was speaking on this topic of brain, how the brain functions mathematically. Most of us were quite lost. Many of us are seasoned mathematicians, but we couldn't follow him. But there is a case there.
It's actually related to cloning.
Yeah.
There's actually a conference series in UK. I wanted to go twice, but I didn't for various reasons. And Roger Penrose was giving one of the lectures. One that's coming up now in September. They have It's called mathematical consciousness.
Yeah. The Fourier thing is a bit limited because it's this what we call a discrete function, Fn. It's like digital cameras that we have nowadays. Everybody raves about how many megapixels and stuff. But the old cameras of the old days did better because they had continuously taking an image. It's like the old debate about CDs and records. Remember we used to have LP records back in the day? They're making a comeback because they give you better sound than CDs. But it was the idea was sold to the public that CDs give you better sound. And somebody who bought a CD player for the first time back in the day said, listen to this here, can you see how crystal clear it is? But actually now they realize that the records are better. So because it was giving you a continuous output as opposed to digital, like one block at a time reading. The Fourier works that way. And things such as, programs like Photoshop, they use Fourier transforms to extend pictures, not to stretch, but to extend. Like if you're drawing a picture with beach and you want a little more beach, you can extend the picture, but it uses the Fourier method. There's lots happening under the bonnet there. Any other kinds of questions? Please go ahead.
The future of that teaching program all about? That's an overall fund.
We've got the expert in the back.
I would like to invite, to answer that, if I may, I would like to invite Dr. Ratulal to the stage. Yes.
Here's the manager of the program. You notice it's a lady mathematician. We're also trying to encourage more girls to be interested in mathematics. Go ahead.
So the Future Mathematicians program, in its pre-launch phase, is a program that we conceptualized throughout this year to launch. And the idea here is that we want to introduce high school learners as well as undergraduate students to essentially the foundations of research mathematics. It's about deductive reasoning, understanding what Professor Janelidze had presented to underlying mathematical structure, the thinking process behind understanding mathematics, talking about mathematics, communicating mathematics. So those are the skills and the underlying processes that we want to essentially deliver through extracurricular activities at high school, as well as workshops, seminars, modules that could be introduced at university level. So we've already started off with an expedition series. So this is all about mathematical exploration. So we'll take you on an expedition led by a champion who delivers content that is created by an architect. And this expedition series is led by a pilot. So we have this, this metaphor that we've created, which tells you that you're going on a mathematical journey. That's the idea here. And so this is the mapping of what a mathematical expedition looks like. And for example, one site could be at a school where we have a pilot who is, well, tomorrow we have an expedition taking place at Star College. Professor Janelidze and myself will be going through. Prof. Janelidze is the pilot of the session. I champion the session, and we're going to be accompanied by a crew. And that's going to be a few postgraduate students, including Shivara Hansraj, postdoc at UKZN at the back. And we have Shimon Corpus, a PhD student, joining us tomorrow. So that's the various stages. What we did already was abstract algebra sessions that we hosted during the April and the July holidays. This was aimed at high school learners. We've got another series coming up in October. And this program, well, in addition to that, those are some of the expeditions that's already taken place. We've already included tomorrow's one on here, and there's going to be a lot more coming in future. But the champions are the people that make the program come together. We've got Dr. Simon Tetwa also listed there as a champion, and that list is growing. So we plan to expand this program and have this reach all areas of South Africa, with students engaging in mathematical exploration via expeditions that champions would have planned. Yeah. That's pretty much the Future Mathematicians program.
So once again, the website is futuremath.net. And if you want, you can join these videos where you can see what we did in these online sessions. It was phenomenal.